the slot of electric machine. The task is to calculate the temperature distribution in the slot of electric machine. And electric machine consists of the stator and the rotor. The rotor is the rotating part and the stator is the motionless part. There are slots in the stator core. In the slots the winding is placed and the electric current is flowing in the winding. We can model only one slot because each slot configuration is the same, so we'll utilize the symmetry of the model and we'll simulate only the single slot. Here you can see it on the left. The setup is the following. There is stator, which is made of steel. There is electric insulation, shown with blue color, and there is the copper conductor. The electric current in the conductor generates heat because of Joule losses, and the heat is evacuated from the stator external surface. This is at the bottom is the external surface, and from the inner surface. Here in the air gap between the stator and rotor. And the heat is evacuated from the cooling duct. All the temperatures at each surface and the convection coefficients are specified. This specific motor is not designed to operate in non-stop mode. It is designed to operate only limited time, and then there should be a period of cooling down to normal temperature. The insulation in the slot can withstand up to only specific temperature. So our task is to find what is the maximum operation time and what time is required to cool down the motor. There is a great difference between the load and the switched off mode. In load mode there is the current in the conductors and the rotor is rotating and the air flow in the air gap and the air flows in the cooling duct. But after we switched off the motor, the rotor is not rotating, there is no air motion in the air gap, there is no air motion in the cooling duct. So the heat is evacuated only from the external surface. Now let's run QuickField and simulate this problem. Here is QuickField window. You can see this is new version 6.3. And I will create the new problem. The problem name is slot 1 and the folder where the project will be stored is here. Next, I should specify the problem type. Well, we would like to calculate the temperature distribution in time, so this will be the transient heat transfer problem. And for transient problem, you should specify the timing. The final calculation time, well, it will be 1800 seconds, which is 30 minutes. And the calculation time step, which is 60 seconds. By default, the initial temperature in transient problem is 0 degrees kelvins. In new version QuickField 6.3, it is possible to specify initial temperature, which could be constant value or the equation. And this is initial temperature is valid for all objects in the geometry model. In our case, the initial temperature is 20 degrees Celsius, so I type in 20 plus 273. 273 is a term that is used to convert from Celsius degrees to kelvins. You see, QuickField operates in kelvins. I will import the geometry model from .exe file. Here you can see the geometry model. In many cases, it works. The DXF import works like this. You just specify the file, and the geometry model is imported very well. In new version, it is possible to specify the tolerance. The tolerance means the ratio of large object to the small object. You see that if you have very small objects, for example, with the ratio of large to the small of about 10,000 to 1, the small objects may appear distorted or be missing. In previous version, you would need to add missing elements manually, but in new version, you can adjust the tolerance ratio, so the small objects will be imported. Again, in most cases, you would not need to do this, but for some specific models, this is useful. Now, in my geometry model, I should assign labels to each geometry object. This is steel. I simply type in the name and press OK button, and the name appears in the tree. Now these two blocks are copper. This is the insulation. And this is the wedge that prevents the winding falling from the starter slot. It's made of some dielectric material. Now these are materials in my model: the steel, the copper, the dielectric, and the insulation. You see, this is the whole, and in transient analysis, in heat transfer analysis, I specify properties only for solid materials. I do not specify properties for the gases and for the liquids. Instead, I should specify the boundary condition. So on this surface, I set the label cooling duct. And remember, we have this heat sink here. This is the external stator surface. External surface. And we have the heat sink here on the internal surface. And here I will set the zero heat flux, because on the left and on the right I have the same slots with the same joule heat. So this will be the symmetry. Zero heat flux. Now I can assign physical properties for each object. I will double click the name in the tree, and here I specify properties for the copper. The thermal conductivity of copper is 380. The specific heat is about, again, 380, and the volume density is 8,900. And we have the losses in the copper because of the current, electric current flowing there. So here I should specify the losses, which are 360 milliwatts per centimeter cube. And I should convert them to watts per meter cube, which is this value. Now for other materials, for the dielectric, I specify the thermal conductivity of the dielectric material, its specific heat, and the volume density. For the insulation again, I specify the thermal conductivity of the insulation, the specific heat, and the volume density. And for the steel, I specify thermal conductivity of steel, the specific heat of steel, and its volume density, which is 7,800 kilogram per meter cube. Now you see there is no more question marks on the labels of the blocks, but there are question marks on the label of the H, so I will specify the physical properties for the boundary conditions. Initially we will simulate the operation mode, so the rotor is rotating and the fan is blowing, and the convection coefficient in the air duct is 80 and the temperature is 20 degrees Celsius. Again, I will add the term 273 to convert to kelvins. For the external surface, again, I specify the convection coefficient, which is 15, and the temperature, 20 Celsius degrees. converted to kelvins. For internal surface, again I specify the convection coefficient. The temperature here is high because there is a rotor rotating which is heating too, and rotor heat up the air in the air gap, so the temperature will be 40 degrees Celsius, and the convection coefficient is 100 because the rotor rotation speed is high. Now on the symmetry boundaries I specify zero heat flux because there is the same slot on the right and the same slot on the left. Now we can build the finite element mesh, save all problem files and run the simulation. And here is the result. You can see the temperature distribution after 30 minutes of operation time. Again, the temperature is in kelvins, so I will convert to Celsius. 350 minus 273, which is 77 degrees Celsius. You can see how the temperature changed in time switching the time layers. Initially it was cold, then after we switched on the current, the temperature rise. You can see the temperature, how the temperature changed in time on the plot. Just double click and choose the time plot. So this is the time plot of the temperature change in time. You can see the temperature drop in the insulation. I will simply use the contour tool, draw the contour here, and open the XY plot. And here you can see the temperature drop in the insulation. Now our task was to find the temperature distribution in time and decide at what temperature we should switch off the operation mode to let the motor to cool down. Now let's presume that we switched off the motor at this moment of time after 20 minutes of operation. And the winding temperature after 20 minutes will be 67 degrees Celsius or 340 kelvins. Now what I would like to simulate next is to find how the motor will be cooling down. To do this, I will create the new problem. Slot 1 underscore cooling. Again, it will be the transient heat transfer problem. I will use the same geometry model, so I will not need to draw it again. So I press the browse button. and choose the same geometry model. And here I will specify the time. Well, you remember we have the poor cooling conditions because the rotor is not rotating and the air is not blowing in the cooling duct. So I will set up the final calculation time to 3,600 seconds, which is 1 hour, and the calculation time is 60 seconds. Well, in this problem I can specify uniform initial temperature because the temperature distribution is not uniform. You can see after 20 minutes of operation the temperature distribution is not uniform. So in my cooling problem I would like to put the link to the heating problem and use this temperature distribution as the initial. So I open the problem properties, my cooling problem properties, follow to the links, choose the link type, the temperature field, and select the problem slot 1, and I add the link. You see, as slot 1 is the transient problem, I can specify the time at which time I would like to read the temperature field. 1020-200 seconds. Now I have the cooling problem set up ready. I use the same geometry model. I put the link to the heating problem to get the temperature distribution after 20 minutes of operation. Well, I can copy the material properties from initial problem. Just press Ctrl C and Ctrl V and the properties will be copied. But remember, this is cooling process, so we will specify 0 losses in the copper conductor, and we will need to adjust the cooling conditions. So I have finished copying label properties, physical properties of material from one problem to another. Now I should correct some properties. For the copper I specify 0 losses because now the motor is switched off. There is no air flowing in the air duct. So again I remove the convection boundary condition. And the rotor is no more rotating and the fan is not more blowing, so I remove the cooling condition on the internal surface. The only heat sink is the external surface of the stator. Now let's run the simulation. Here you can see the temperature distribution after 1 hour of cooling down. Now let's see how the temperature changed in time. It was 67 degrees Celsius and after 1 hour it cooled down to 39 degrees Celsius. So 1 hour is not enough to cool down this motor. You will probably need to run the simulation with the longest final simulation time.